Welcome to Astronomy Daily. I'm Anna.
And I'm Avery. It is Friday, the 24th of April, and we have got a genuinely remarkable show lined up for you today.
We do, and I want to kick things off with something that had the whole team talking this morning. Scientists have just published the first ever chemical analysis of water inside an interstellar comet, and what they found is extraordinary.
We're talking about our old friend 3I ATLS, the interstellar visitor that swept through our solar system last year. And the verdict from astronomers, it came from a world that was much colder than ours.
Much colder, like almost incomprehensibly colder. We have that story, plus what's been feeding the supermassive black hole at the heart of our galaxy. That mystery may finally be solved.
Japan has a spacecraft sitting on a launch pad right now, ready to head to a tiny moon of Mars and bring a piece of it back to Earth. And tonight, Aurora watchers in Australia and New Zealand, keep your eyes on the sky.
All that, and we're asking the big question, could aliens already know that we exist? The answer might actually be yes.
It's a big one. Let's get into it.
Our lead story today is a world first, and it involves the interstellar comet that captured everyone's imagination when it swept through our solar system last year.
3I ATLS, the third interstellar object ever detected passing through our neck of the cosmic woods. And now scientists are telling us something truly jaw-dropping about where it came from.
A team led by PhD student Luis Salazar Manzano at the University of Michigan, working with colleagues at the ALMA telescope in Chile, has made the very first measurement of deuterated water, what's sometimes called semi-heavy water, inside an interstellar object.
Okay, for anyone who slept through chemistry class, what exactly is deuterated water?
Great question. Though regular water, H2O, has hydrogen atoms with just a proton at their core, but deuterium is a heavier form of hydrogen that has both a proton and a neutron. When you swap one of those regular hydrogen atoms for a deuterium atom, you get what scientists call HDO, semi-heavy water, or deuterated water.
And the key thing is, the ratio of heavy water to regular water in a comet tells you about the temperature of the environment where that comet originally formed.
Exactly. Cold, low radiation environments produce more deuterium-rich water. And 3I Atlas, it's loaded with it. The ALMA measurements show it contains around 30 times more semi-heavy water than any comet in our own solar system, and 40 times than Earth's oceans.
40 times. That's not a small difference.
It really isn't. And what that tells us is that 3I Atlas formed in an environment that was utterly unlike the early solar system, likely somewhere extremely cold, well below -240 degrees Celsius, in the outer reachings of some distant planetary system, or possibly in a primordial interstellar cloud.
And there's more intrigue here, because some researchers think 3I ATLS could be up to 10 or 12 billion years old, which would mean it formed before our sun even existed.
Which makes it, in the words of one of the researchers, a preserved fragment of an ancient planetary system, a fossil from the early Milky Way grifting through our neighborhood.
Harvard astronomer Avi Loeb has raised the characteristically eyebrow-raising question about the abundance of deuterium, noting that deuterium is actually fusion fuel, and wondering out loud whether that overabundance might be a technological signature, although he admits that's highly speculative.
Very speculative, but fun to think about. The paper is published today in the journal Nature Astronomy, and it also marks the first time any team has successfully performed this kind of chemical analysis on an object that originated beyond our solar system.
Each interstellar comet, as one of the researchers put it, brings a little bit of its history, its fossils from somewhere else in the galaxy. And with instruments like ALMA, we're starting to actually read those fossils.
A landmark result. And they say this now opens the door to doing the same chemical fingerprinting on future interstellar visitors. So 3I-Atlas may have set a new template for how we study objects from beyond.
Okay, next up. A mystery that has puzzled astronomers for decades may finally have an answer. And it involves the 4 million solar mass black hole sitting at the very center of our galaxy.
Sagittarius A star. the sleeping giant at the heart of the Milky Way.
For years, astronomers have been watching strange gas clouds drift towards it along almost identical paths. Gas clouds called G1, G2, and the newly discovered third cloud, informally known as G2T, and nobody could work out where they were coming from or why they were on such remarkably similar orbits.
Until now, a team of researchers led by the Max Planck Institute for Extraterrestrial Physics using the Very Large Telescope in Chile has cracked it. And the answer is delightfully dramatic.
Go on then.
Two massive stars, locked in what the paper describes as a violent embrace, a binary star system called IRS-16SW, located near the Galactic Center, whose powerful stellar winds continuously shed enormous amounts of gas.
And as IRS-16SW orbits Sagittarius A star, each ejection of gas gets flung out in a slightly different orbit, which explains why G1, G2, and G2T are on almost identical paths, but rotated a tiny bit relative to each other.
Exactly. And crucially, the team's calculations show that the infall of just one such clump, roughly the mass of Earth every decade, provides enough material to sustain Sagittarius A star's current level of activity.
So it's not some exotic, mysterious process. It's just two stars in a wild gravitational dance constantly shedding material that slowly trickles down into the black hole.
It's a beautiful result because it connects three things that astronomers study separately: stellar evolution, gas dynamics, and black hole feeding into one consistent picture. And it suggests that star formation and black hole growth may be intimately linked, even in our own galaxy.
And the discovery also rules out a previous theory that each of those gas clouds might be hiding a star at its core. Given that G1, G2, and G2T are all on practically identical orbits, the odds of three separate stars independently ending up on those paths are essentially zero.
Right. They must share an origin, and IRS-16SW is the most compelling explanation. The research is published in the journal Astronomy and Astrophysics.
Before we move on to our next story today, just a quick reminder to support our sponsor NordVPN and do yourself a great big money-saving favor. Get secure online for less with the service we use, NordVPN. I can't recommend them enough. Check out our special listener deal by clicking on the link in the show notes.
Now, a mission story that we've been keeping an eye on for a while, and one that has a very special connection to our part of the world.
Japan's Martian Moons Exploration Mission, MMX, has officially arrived at the Tanegashima Space Center and is being prepared for launch later this year. We're talking November or December 2026.
And the destination? Phobos, one of the two tiny, lumpy moons of Mars. MMX is going to fly to Phobos, land on it, drill into it, and bring back pieces of it to Earth.
The first ever sample return from the Mars system, which is pretty extraordinary when you think about it.
It is, and this mission has had a rocky road, no pun intended. It was originally supposed to launch in 2024, but ran into problems with Japan's H3 rocket. There was also concern after a second H3 failure in December 2025, but that issue was isolated to a payload fairing problem, not the rocket itself, and the path was cleared for MMX to proceed.
So what's the mission going to actually do once it gets there?
MMX will arrive in orbit around Mars in 2027 and spend time mapping both Phobos and the smaller moon Deimos. Then in 2029, it will actually land on Phobos and collect about 10 grams of surface and subsurface material using two different sampling systems.
10 grams doesn't sound like much, but sample return missions have taught us that even tiny amounts of pristine material can be enormously scientifically valuable. Japan's Hayabusa 2 mission returned barely a teaspoon of material from the asteroid Ryugu, and scientists are still extracting discoveries from it.
The big scientific question MMX hopes to answer is, how did Phobos and Deimos actually form? Were they asteroids captured by Mars's gravity from the outer solar system, which would mean they should be rich in water and organics, or are they debris from a giant impact on young Mars, in which case the heat would have driven off any water?
And the answer has implications for understanding how the inner solar system formed, and possibly for the origins of life on Earth.
Now, here's the detail that I know will resonate with our Australian listeners in particular. When NMX returns to Earth in 2031 with its precious cargo,
The sample return capsule lands in Australia, specifically the Woomera Prohibited Zone in South Australia.
so there's a direct connection for us. Phobos material delivered to Australian soil. That's something to look forward to.
MMX also carries the IDEX rover, built jointly by the German and French space agencies, which will actually drive on Phobos. Given that gravity on Phobos is about 1,800 times weaker than on Earth, that'll be quite a drive.
An audacious mission. It's on the pad, the clock is running.
All right, I love this next story, partly because of the job title. Stellar Archaeologists. That's what the researchers behind it are calling themselves.
Which is a fantastic job title. And what they found is genuinely illuminating, not just for understanding stars in general, but for understanding the future of our own sun.
So, what's the discovery?
Scientists at the Institute of Science and Technology Austria have found what they're calling fossilised magnetism on white dwarf stars. And they've used that to build a new model that explains how magnetic fields behave as a star evolves from a bloated red giant all the way through to a cold, dense white dwarf.
For listeners who need the refresher, a white dwarf is what our sun will eventually become. In about 5 billion years, the sun will exhaust the hydrogen in its core, puff out into a red giant, probably swallowing Mercury and Venus in the process, and then shed its outer layers, leaving behind a dense Earth-sized remnant called a white dwarf.
And what this research does is connect the magnetic field that we can detect at the core of a red giant using a technique called astroseismology, which is essentially starquakes, to the magnetic field that appears at the surface of a white dwarf billions of years later.
Doesn't disappear or reset, it's preserved. It travels with the star through its entire evolution from red giant to white dwarf, and then re-emerges at the surface, hence fossil magnetism.
And interestingly, the team found that older white dwarfs tend to be more magnetic than younger ones, which fits neatly with the fossil field theory. As more of the star's interior becomes magnetized over time, the field gradually spreads to the surface.
So what does this mean for us, for our sun?
Well, it deepens our understanding of how stars like the sun evolve in their final stages. Magnetic fields play a significant role in how a star's interior works and how long it lives. By understanding how those fields persist and transform, we get a much clearer picture of what the sun's twilight years will actually look like.
Which is still 5 billion years away, so I'm not immediately worried.
Probably not your most pressing concern today, no. But it's a beautiful piece of science, connecting observations of different stellar life stages across billions of years of cosmic time. Stellar archaeology, indeed.
Indeed. And I hope this helps answer some questions for our listeners. We do get a lot on this subject.
Now, a story that I think is going to spark some very interesting conversations. And the premise is simple but profound. If there are intelligent civilizations out there looking for signs of life in the universe, they may already have found us.
Which is either very exciting or mildly terrifying, depending on your point of view.
Possibly both. The thinking goes like this. When we search for signs of intelligent life, what do we look for? We look for technosignatures, evidence that a civilization has modified its environment in detectable ways.
Radio signals, laser pulses, chemical signatures and atmospheres, things that couldn't plausibly be produced by natural processes.
And the key insight is Earth already has a lot of those. Our planet has been broadcasting radio waves into space for over a century. Those signals have already reached more than 1,000 nearby stars.
Including Proxima Centauri, Vega, Barnard Star. If there's anyone listening around those stars, they've potentially been receiving our broadcasts for decades.
And it's not just radio. Earth has enormous human-made structures that might be visible to sufficiently advanced telescopes. Huge solar farms covering dozens of square kilometers. City lights visible from orbit. The chemical fingerprint of industrial activity in our atmosphere.
So the question flips from, are we searching for them, to have they already found us?
Right. And researchers studying this angle suggest that what we call technosignature detection from our end, the tools we'd use to find alien civilizations, are exactly the same tools an alien civilization would use to find us. We're not hidden.
There's something both humbling and thrilling about that. We've been sending out our calling card for 100 years. Whether anyone's received it and decided to respond is, of course, the great unanswered question.
The SETI Institute is actually working on updated protocols right now for what happens if we do receive a confirmed signal, a declaration of principles that would govern how scientists announce the discovery and how humanity responds. That's being finalized at a major international conference later this year.
So the scientific community is quietly, methodically getting ready, which I find rather reassuring.
Me too. The universe is a big place. The question of whether we're alone in it is one of the oldest and most profound that humanity has ever asked. And the answer, one way or another, could come from someone finding us first.
And finally today, a story for the sky watchers among you. And if you're in Australia or New Zealand, listen up, because there's something potentially beautiful on offer tonight.
A coronal mass ejection, a CME, from an eruption on the sun earlier this week is delivering a glancing blow to Earth right now, today, on the 24th of April.
To give a bit of context, a few days ago, two filaments on the sun erupted simultaneously in opposite directions, a pretty dramatic solar display. One of those eruptions sent a wave of charged solar material in our direction.
It's only a glancing blow, not a direct hit. But combined with fast solar wind from a coronal hole that's been rattling Earth's magnetic field for several days now, conditions are elevated. We could see G1 minor geomagnetic storm levels. That's a KP index of 5.
And G1 conditions can push auroras to lower latitudes than usual. So if you're at a higher latitude in the Southern Hemisphere, southern parts of Australia, South Island, New Zealand, Tasmania, and you've got clear skies tonight, it's worth getting away from city lights and looking south.
There are no guarantees with auroras. They're unpredictable by nature. But the conditions are more favorable than average. Check the Bureau of Meteorology's space weather alerts or the spaceweather.com website for the latest KP index readings throughout the evening.
And even if the aurora doesn't materialize, there's a bonus in the southern sky right now. Comet C/2025 S3 Pan-STARRS is approaching its closest point to Earth on April 27th, just 3 days away. It's estimated to reach around magnitude 7 or 8, which means binoculars or a small telescope should show it in the evening sky in early May for Southern Hemisphere observers.
So eyes to the south tonight, aurora conditions, and a comet on approach. Not a bad Friday evening, all things considered.
Not bad at all.
And that brings us to the end of today's Astronomy Daily, Season 5, Episode 92.
What a show!
An interstellar comet carrying water from a billion-year-old frozen world? The secret of what's feeding the Milky Way's most famous black hole? Japan's audacious mission to Mars's moon, with the return capsule landing in Australia.
Stellar archaeologists decoding the future of our sun, the sobering and exciting possibility that aliens already know we exist, and a solar storm making a run at our magnetosphere as we speak.
If you enjoyed the episode, please leave us a review wherever you listen. It makes a huge difference for an independent show like ours.
Find us on X, Facebook, TikTok, YouTube, Rumble, and Instagram at Astro Daily Pod. And visit astronomydaily.io for show notes, transcripts, and links to all the research we covered today.
From me, Avery.
And from me, Anna, clear skies, curious minds.
Astronomy Daily.